Hello everyone. Thank you so much for joining my session. My name is Ravi. I work at Samsung as an engineering leader while contributing to the Go ecosystem and also maintain few security tools. I'm based in California. Today I am presenting my paper Go Safe Input. It is a zero dependency input sanitization framework that can be used directly for digital forensics and cybersecurity applications in Go. If you want to follow along or explore the code during or after this talk, the framework is publicly available on my GitHub repo. Please feel free to check it out. Over the next few minutes, I will walk you through the problem. Uh, Forensics tools generally process adversary control data at volume, and it also makes them uniquely exposed to injection attacks. MyTrace own data confirms these are not just theoretical risks. There are almost 41 known exploited vulnerabilities across the exact four category forensic tools face daily. I will then show you the gap, and generally Go does not have a single library that covers all these aspects without external dependencies. That's actually what motivated me to write Go Save Input and also open source it. From there, we will see the design, implementation, security evaluation, performance, and also how it is easy to integrate these patterns into real forensics workflows, and also three case studies. And also, we will see some limitations, the supply chain implications, and the future roadmap. Well, by the end, I'm hoping that you would not just see what GoSafe Input does, but you will also see why it was built this way so that it performs under real conditions and how forensics can make use of this tool. So why do forensics tools need dedicated input sanitization, right? Like unlike typical enterprise applications, forensics tools are designed to process adversary control data. Every piece of evidence you analyze could be a weapon aimed at your own workstation. Consider these four attack surfaces. For example, the first one, evidence processing. Imagine a zip file seized from a suspect might contain a file name like dot dot slash dot dot etc password. If your tool passes that unsanitized to the file system, you have a path traversal attack. Second, case management interfaces. Right? When investigators enter case IDs or search for evidence, those inputs can carry cross-site scripting or SQL injection payloads that compromise the entire case database. Third, chain of custody. If a forensics platform is exploited, evidence integrity is compromised, obviously, right? Defense attorneys can challenge findings from any tool with a known vulnerability. And fourth, examiners are now being directly targeted. We are seeing malware samples that contain strings specifically crafted to trigger command injection when passed to tools like exiftool or strings. And that is a reason why forensics tools need something more rigorous than a generic web app sanitizer. Let me put some numbers behind the threat. MyTrace 2025 CW Top 25 analyzed almost 39,000 CV records and identified 41 known exploited vulnerabilities, especially across these four injection categories. Cross-site scripting is ranked number one in the entire list, not just among injection types. SQL injection is number two, and command injection has 20 active exploited vulnerabilities in the wild right now. Path traversal has 10. These are not just theoretical vulnerabilities. The KV designation means they have been actively exploited in real attacks in the real world. For forensics, the mapping is direct, right? The XSS threatens your case management web interface. SQL injection targets your evidence database and hash catalogs. Command injection is a risk when your pipeline calls out to tools like exiftool or file with evidence derived arguments. 41 actively exploited vulnerabilities, all of them are relevant to the tools you are doing every day in your digital forensics lab. So where do these existing Go sanitization libraries fall short? I looked at the most commonly used options. Blue Monday is excellent for HTML sanitization, 98% of XSS coverage, but it does nothing for SQL injection or path traversal or even command injection. And it introduces three direct dependencies with 8 transitive ones. HTML template handles XSS at 95%, again, nothing else. File path. So Basically, there is no single library that is handling all these four categories, and developers are ending up stitching together multiple libraries, and each one adds supply chain risk. For forensics tools, every dependency is a liability. The entire source code of your tool needs to be auditable for court testimony. If you cannot account for every package your binary contains, your tool may be challenged. So that is the reason why this co-save input will solve this. One library with all these four categories with zero dependencies, and every line is auditable. Well, this is built under like five core design principles that emerge directly from the requirements of forensics and security tooling. The first important goal is that we should have a better comprehensive coverage, right? Encompassing all these four injection categories. And in future, there may be new categories, so we can keep adding. So there is no mixing and matching of each individual rules. And it should also be a context aware. So the developer must explicitly tell the framework what kind of input they are sanitizing. You can't accidentally use the wrong sanitizer for the wrong context. If you pass the wrong context, you get an error. So not a silently sanitized, but still dangerous string. Our goal three is zero dependencies because we don't want to externally depend on some other binaries or packages, libraries. So whatever comes out of the box from the language itself is what I have used. The goal four is most important, which is the forensic integrity, meaning that, if at all there is any failure, like we have to have some fail secure defaults. If the framework detects a traversal pattern or an injection sequence, it immediately returns an error. So it never tries to clean a suspicious input and pass it through silently. Our goal five is about performance. Because if you notice, these forensics labs process evidences at volume, so we need sub-millisecond overhead. That wouldn't become like a bottleneck. So yeah, let me walk you through these three layers of this architecture. At the top, you see the AP layer, which is exposing a single function, sanitize. The developer passes in the untrusted input string and an explicit context enum. That's the entire public interface, simply intentional and also impossible to misuse without getting an error. The middle layer is a context router. It reads the context parameter, validates and dispatches to the correct sanitizer. If the context is invalid or unrecognized, the router returns an error immediately. So this is more like a fail secure behavior. At the bottom, the implementation layer contains 6 specialized sanitizers: HTML body, HTML attribute for XSS, SQL identifier, and SQL value for SQL injection, file path for path traversal, and shell arg for command injection. So all these 6 are implemented using only 5 packages from Go standards library. So there is no external package, or there is not even any transitive dependencies. Let me walk you through two of these 6 sanitizers in detail. Look at the path traversal prevention, which is very, very critical, right? Especially when you're doing a forensics archive extraction. When you unzip a file seized from a suspect, every file name inside that archive could be a weapon. The traversal pattern slice contains every known variant, basic dot dot, URL encoded variants like percent, dot encoded forms, double encoded sequences, and filtered by passes like 4 dot slashes. So beyond pattern matching, we also check for null bytes, a classic technique where attackers append null bytes after a traversal sequence, hoping the language string handling truncates at the null. And we reject any absolute paths entirely, and any hit on any of these checks return an error. So basically, again, we are failing fast. We never try to clean and continue. For command injection, the key design decision was to use an LO list rather than block list. With a block list, you specify what's forbidden, but attackers constantly discover new meta characters and encoding tricks that bypass your list. With an LO list, you specify exactly what's permitted: alphanumerics, hyphens, underscores, and dots. Everything else is stripped before the string ever reaches exec.command. This is the only approach that is provably safe when calling external tools like exif tool strings or file on evidence derived file names. For the XSS sanitizer, we use a two-pass approach. The first pass strips dangerous content using compiled regular expressions, script blocks, iframe blocks, OnStar event handlers like onClick equals and JavaScript colon URI schemes. The second pass applies Go standard HTML escape string to encode any remaining HTML entities, This is important for forensic web interfaces that display evidence metadata like EXIF data, file system entries, or case notes, any of which could contain container controlled content if the evidence was crafted to exploit the investigator. For SQL injection, the focus is on the identifier validation. It is essentially used when forensics case management systems need to build dynamic queries with column or table names that cannot use parameterized queries. The approach is strict regex validation. Identifiers must start with a letter or underscore, contain any alphanumerics or underscores, and it should not be longer than some predefined 63 characters. Generally, if you're using a Postgres identifier, there is a limit, and reserved word check could be used to catch any injection attempts, like for example, drop or union. I want to be very clear that parameterized queries are always preferred for SQL values. The SQL identifier addresses the gap where identifier names must be dynamic. Well, our security evaluation comprised of 530 attack payloads from 4 different sources. OWSAP test guide, payloads, all the things, hack tricks, and custom payloads targeting forensic specific scenarios. We saw a phenomenal improvement in the results. 150 XSS payloads, which were like 100% detected and blocked, 200 SQL injection payloads with 100% accuracy, 100 path traversal payloads, including URA encoded and double encoded, and filter bypass variants. For comparison, we noticed that Blue Monday achieves just 98% on XSS, and FilePath Clean handles 72% of path traversal, and there is no single Go library that actually does 100% across all these categories. On a important note, I would like to highlight the path traversal result particularly because that's the 100% including encoding bypass variants. And generally filepath.clean misses like %2, or some flotation encoded sequences are missed. So these are exactly the tricks that attackers embed in file names on seized media to exploit forensics tools. Let's talk about performance, because even a perfect sanitizer it uses makes your evidence pipeline too slow, right? So we benchmarked on the AMD EPV YC7763 server with Go 1.22, and all measurements are median and tail latencies. The fastest operation is in the SQL identifier validation. It runs at sub-millisecond mean, even file path and shell argument and HTML body. At the 99.9th percentile, the absolute tail HTML body stays at sub-millisecond. Everything else is well under half a millisecond. To put it in that context, if you are processing 840 million evidences like the enforcement lab in our case study, the sanitization overhead is under 2 minutes of total added latency. That's pretty much negligible. Our integration testing with REST API workloads at 50,000 requests per second confirmed that 2% throughput overhead, which is not a big deal, especially it's not like a bottleneck at all. And here's how GoSafe input looks into real integration code. The evidence processing pattern on the left is the most critical to get right. First, extracts the base file name using filepath.base. This gives you just the file name without any directory component. Then it sanitizes with the file path context. If sanitization fails, it returns immediately an error. I mean, basically, you just don't skip, you just return. We build the output path using filepath.join, which adds another layer of safety. And when calling an external tool like EXIF tool, it sanitizes the argument again with shell argument. And because the file path and shell argument context enforce different rules, a file name say for the file system might still contain characters that inject into a shell command. The case management pattern on the right shows defense in depth. Sanitization in the case IDs with SQL identifier before any database query. Sanitize the node's content with a HTML body before rendering. If either false, return HTTP status code 400. Notice that these are different contexts. The ID needs identifier validation rules. The nodes need HTML sanitization rules. That's the context awareness in action. For threat intelligence pipelines, the key insight is that malware others know their samples will be analyzed and they craft them to exploit analysis tools. So let's move on. Well, we actually validated these in three production environments: security vendor, running an endpoint detection platform, monitoring 50,000 system daily, and collecting file metadata, registry entities, and processing information from compromised endpoints. Second, an enforcement digital forensics laboratory. Over 6 months, they processed almost 840,000 evidence items. The framework actually blocked close to 2,300 malicious payloads across archive extraction, EXIF metadata display, and automated report generation. That zero is the number that matters in code, right? Um, Finally, threat intelligence company analyzing our malware samples. Their challenge was very unique. The malware itself is the attacker. Every string extracted from a sample, every file path observed during dynamic analysis must be treated as hostile. With Go Safe Input sanitizing all IOCs before database storage or pipeline processing, they had zero exploit escapes from the analysis sandbox. Well, the zero dependency design deserves its own dedicated discussion because for forensic tools, it's not just about convenience, it also has legal implications. Look at the table. Blue Monday introduces 11 packages into your dependency graph. Go Playground validator brings 20. Every one of those packages is code, so you did not write, can't be fully auditable, and may not be able to defend in a code room. The 2018 event stream incident demonstrated exactly how this plays out. A widely trusted NPM package was quietly compromised to target a specific application. The same risk exists in Go. If even one transitive dependency in your forensics tool is compromised, evidence integrity is in question. So when defense counsel asks, and they will ask, right, what software was used to process this evidence? And is that software trustworthy? You can answer yes, and you can always prove the evidence. Let me close with where GoSafe Input is heading towards. The first priority is automated context inference. Currently, developers must manually specify the sanitization context, which is correct behavior, but it requires developer knowledge. We are working on the IDE plugins and static analysis tooling that can analyze where input string flows and suggest the appropriate context automatically. We also want to diversify these across other languages like Python and Rust. We want to port it. Third, I would like to formally integrate with, possibly with NIST computer forensics tool testing program. This is a path to certified deployments in some of the law enforcement and legal contexts. And fourth, extending coverage to XML external entity, injection and server-side request forgery. As forensics tools increasingly process complex document formats and cloud-sourced artifacts, these vulnerability classes become more relevant. You can follow the development in my repo. So let me bring this together. Go Safe Input provides a unified auditable solution to the injection vulnerability problem in digital forensics and cybersecurity applications. It is 100% detection rate across 530 attack payloads, a less than 2% throughput overhead at 50,000 requests per second. Again, as I said, zero external dependencies, and all these results have been validated, and the framework is open source and available right now. I would love to hear from anyone in this room or whoever is working on forensics tooling to connect with me on LinkedIn or email me directly. Thank you once again for your time.